All right. Welcome, everybody. This is our first lecture of 2021 and the spring semester of this academic year. We're really excited to see you all. Just some quick information. So Science in the News, we are a student organization, graduate student organization at Harvard. We do lots of things alongside these lecture series. Our goal is to kind of make science accessible, share our work, and also have graduate students get practice sharing their work with the greater community. And this is one of our sort of biggest outreach activities where we do sort of weekly or once every 2 weeks lectures on very, very different science topics led by graduate students. Some logistics about today. So you might be listening to me on Zoom or on YouTube. Both exist. So if Zoom fails you, you can go to YouTube. If YouTube fails you, you can come to Zoom. Have both of those options in your mind. So the way the lecture will work, we'll have 3 sections. Each of them will be 15-ish minutes. And then we'll take a few 5-minute breaks between each, little bio breaks for you to go get water, do whatever you need. And questions we'll be asking, we'll have time for questions at the end of each of these 3 sections. So write those in the chat. If you are on Zoom, we could unmute you if you want to ask it verbally. But if you can also just write it in the chat, and me and Lillian, who's our other moderator, will voice it out to our speaker. And you can also ask questions on YouTube. So if you're on YouTube, we're watching all of those. So everything is being watched. So I will hand it over. So our first lecture is super exciting. Happy belated Valentine's Day to everybody. So today we'll be talking about the love between stars and black holes. And I'll let Flora introduce herself.
Yeah, thank you so much. Welcome, everyone. I'm very happy to be here and share with you one of my passions, which is astronomy and especially black holes. But first of all, I thought, why not start with telling a little bit about who I am? So I would kind of describe myself with the following 3 pictures. So I'm a graduate student originally from the Netherlands, from Amsterdam. And I love these cookies that are called stroopwafels. If you have ever the chance to try them, do so. They're very delicious. I never really was interested in physics until I started reading Stephen Hawking's book, The History of the Universe. And that literally blew my mind and really got me interested into like black holes and astrophysics, and eventually became one of the reasons why I am now a grad student at Harvard. And in my free time, I really like juggling. So usually if the talk wouldn't be live, I would actually juggle during the talk to demonstrate some of the stars and their relationships. But you'll have to like attend a different talk in the future, hopefully, for that. So today I want to talk about exceptional marriages among the stars. And probably for most people, when you think about exceptional marriages among the stars, you maybe think about Kanye West that just broke up, or Angelina and Brad Pitt who also just broke up. And then maybe some couples that you're very familiar with that have these 10-year relationships, which usually for celebrities is already very, very impressive. However, if you would ask me about what are exceptional marriages among the stars, I see a picture that looks more like this. This image is trying to show 2 black holes that you see in the middle staring at you that are just almost going to merge and collide with each other. And I hope that at the end of this talk, you'll all be able to understand why these type of black holes, a pair of black holes that is merging, actually is kind of the remnants of the longest marriages in our universe, namely marriages of billions of years of stars that are together for billions of years and eventually can form these black holes that we see in this picture. But we'll discuss that during the remaining talk. And throughout the talk, I always imagine myself kind of as this detective, like a space detective. Because why is this interesting? Well, we want to study these black holes and these long marriages for one main reason. because these type of marriages among the stars that form these merging black holes, they're one of the longest existing relationships in space. And so by observing these and studying these, we, like I as an astronomer, we can actually learn something about the past of our universe, because they basically allow us a way as a detective to look back and see how these stars live throughout time and in our universe. And one of the key questions that I especially like to answer is, how did these black holes once form? And as a side question, how many of these black holes actually live in space? And we'll get there, so don't worry if you're a little bit confused by now. And we're actually going to get there through this little scheme. So the total lecture today consists of 3 parts. In part 1, I'll explain what black holes are and what these gravitational waves are that you saw on my title slide. In the second part, we'll discuss how some stars live a happily ever after and how most don't. And then in the last part, we'll try to find the secret behind these matches made in heaven, namely the stars that live forever and can form these pair of black holes, and what this has to do with playing the game Battleship. So hold on tight. But let's first start with this first part. What are black holes and what are gravitational waves? Well, to explain what a black hole is, we first have to look at stars and how stars live and die. And we can, for instance, think about a star like the sun. And in most cases, people would maybe draw something like this, a yellow star that might be the sun. However, in real life, stars are not star-shaped. That's actually a big misconception, but they're actually a sphere. And stars like the sun, they actually consist of 2 parts. In the center, there's a core where the star burns fuel, so burns in this case hydrogen into helium. And that's how a star like the sun actually can produce light. And then around it is this yellow envelope, which is just a big gas layer that is around this core where it's burning. And stars like the sun can live for many billions of years, but eventually in something like 10 billion years, which is an extremely long time, they'll burn out of their fuel. And what happens then is that they become really big, like the envelope will expand and become redder. And eventually it will expand so much that it can actually escape. And while this is happening, the little core actually shrinks a bit and becomes more compact. And what you end with in the end is a tiny compact star, which we often call a white dwarf. And so this is also the fate of our own sun. So our sun, in a couple of billion years, will eventually form this tiny compact star. Now, the life is a little bit different when you have a more massive star. So in this case, I'm talking about stars that are 10 times the mass of the sun, of our own sun. In that case, you still have a star that consists of a core and an envelope. The star is now hotter as it even burns more fuel, and therefore it looks a little bit blue. Just like flames, blue flames look blue because they're hotter than the orange part of a flame. Now, eventually, these massive stars also run out of fuel, and it actually happens already after a couple of million years. And in those cases, they also form these red giant stars where the envelope expands, and these are even bigger than with these small stars. And in this case, it's such a massive star and so much is happening in the core when it's dying that now it will end its life in a supernova. So a super, super bright explosion as it is shedding away these outer layers. And what we're end with is that this core becomes compact and compact, but now there's so much mass that it becomes so compact that it forms a black hole. And so if you would ask me, what is a black hole? I would say this. A black hole forms when a massive star dies in space. They are extremely compact objects from which no light can escape. And they form in energetic explosions called the supernova. And I made a picture of one here. So they're very compact. But how compact is that? To give you an idea, in order to make a black hole, I would have to push the entire mass of the Earth into the size of a ping pong ball. That's how insanely compact these objects are. There are a lot of mass that you have to compress into a very, very tiny object. And that's also why they only form in these supernovae, where there's a lot of pressure to form such small objects and compact objects. Okay. But now the next question is, how many black holes are there? Well, for this, I'm going to use a little bit of your help. So if I walk outside and I look at the night sky, I typically see something that looks not as good as this, but I can see maybe a little bit of the Milky Way and then a lot of stars. And so the Milky Way is just a lot of stars that live in our own neighborhood. And it's estimated that in our own Milky Way, there are about 100,000 million stars. So it's about 100 billion. And that's a lot of stars. But my question to you is, so I just told you that these massive stars, they form black holes. So how many black holes do you think exist in our universe? And we're going to do a little poll here. So I have multiple choice questions. Do you think there are 0 black holes thought to exist in our universe? Then please choose A. Do you think it might be about 10-ish? C is around 10,000, and D is 100 million. See a lot of answers in the poll. Ooh, it's very even among answers B, C, and D. That's exciting. I see C is winning a little bit. So the correct answer is that we think there are about 10,000. Sorry, 100 million. Sorry. Answer D. So let's see. So yeah, so about 20% had the correct answer. Ooh. Are you seeing my polling thing or no? Oh, how do I? Oh, okay, I see it. Okay, great. So about 100 million, that's a lot. And usually how I remember it is that it's about the same number as the number of kangaroos on Earth, which is a lot, right? So the next thing is then, can we observe them? Well, there is one way, for instance, to do it. So already in the 1970s, scientists discovered that if you have a black hole that is surrounded by a disk of gas, it can actually eat some of the gas from this disk. And then as this is happening, the gas in the disk can light up and send out these X-rays, which are the same X-rays when you go for an X-ray scan. And so although a black hole doesn't emit light because it's black and no light can escape, this gas around it that it can eat can actually light up. And usually such a disk comes from, for instance, a fellow star that is nearby. And this light is something we can observe with telescopes. And so this is a way to see those black holes, even though they otherwise look dark and you wouldn't see them. And so this is just a little cartoon, but an artist's impression is given here, which looks a little bit like this. So this is the companion star. You'll see more about that, and we'll talk about that later. And here you see the blue disk that is lighting up from these X-rays and emitting these, or shining in these X-rays, as it is eating, as the black hole is eating from the disk and from the companion star. And so these X-rays that you see light up, that's something we can observe with telescopes on Earth. Now, let's do another question. So the first detection of such a black hole through these X-rays was in 1971. And since then, in the past 50 years, astronomers have been looking and looking with their telescopes at the night sky to observe these type of X-rays. And my question for you is, so until 2015, and so since 1971, how many of these 100 million black holes have we observed through X-rays? Is that A, 1, B, a couple of tens, C, several thousands, or D, almost all of the 100 million? Ooh. Okay, I see everyone answered it. Interesting. So most of you thought a couple of tens, and a couple of you thought like 1,000 or almost 100. Can I? Yeah. So the correct answer is a couple of tens. And so after looking for 50 years, and out of all those 100 million black holes that must be out there, we've only seen a couple of tens. And the reason is that they have to be like eating, which they only do rarely. And the other reason is that actually these X-rays, they're not so bright. So it's really hard to find them on the sky and to measure them. And so this is a problem, because if we want to learn about black holes and learn how many there are, we need to have more. Because imagine, for instance, that you're a biologist and you're studying kangaroos. And out of those 50 million that are out there on Earth, you've only seen a couple in the zoo. You probably agree with me that that doesn't give you a really good picture of what kangaroos are like and what their different species are. So we need something else. But luckily, as you already saw in the date, something special happened in 2015. So this happened. All of a sudden, we had all these new detections of black holes. And how come so? Well, in 2015, for the first time, we saw two black holes collide. They were dancing around each other and eventually merged into one black hole, like this little cartoon. And as they did so, they emitted gravitational waves. Now, what are those? Well, we first have to start with, what is gravity? So gravity is something that Newton was already thinking about and is famous for with his apple experiment. And he said that basically everything that has a mass in space attracts other objects with mass. So for instance, the Earth attracts humans, and that's why we stay on the Earth. And this attracting force between objects is what we call gravity. Now, in 1916, then, Albert Einstein kind of expanded on this theory. So he suggested that how you can view this is that basically space is a big trampoline, and everything with mass is kind of pulling on the trampoline and like weighing on the trampoline and causing these bubbles. And he posed in 1916 with his general relativity theory that everything with mass can bend space. And then as a result, he predicted that then if you have masses that are accelerating, so they're changing in speed, and they're kind of like going around as if you would jump on a trampoline or move very fast on a trampoline with two objects, that this would create gravitational waves. And so he predicted that in 1916 already. And so gravitational waves are defined as masses that accelerate in space. And these waves, they move through space with the speed of light and are called gravitational waves. And so although he already proposed this in 1916, it still took astronomers almost another 100 years to build detectors that could actually find these and measure these gravitational waves. And so in 2015, for the first time, such a collision between black holes was measured. And this is just a cartoon, but what it looks like, if you have some visual video, is something like this. So here I'm showing two black holes that are orbiting and colliding eventually with each other. And in green, you see visualization of these waves in space. And now they've merged into one black hole, and you can see that the waves are traveling through space and will eventually reach the Earth. And so as they do, they move the Earth. The waves are passing the Earth, and they actually move and squeeze the Earth up and down. And this is something that scientists can measure. And so in the past 50 years, these three men, companioned with 1,000 scientists, have worked really hard to build a detector to actually measure those waves. Because the problem is that although everything that has mass and gravity that is accelerating produces these waves, only extremely massive objects can get it. And so they built an instrument, and in 2015, for the first time, the instrument was precise enough to measure them. And they actually won the Nobel Prize for it in 2017. And to give you an idea of like how precise these detectors must be, it's basically the same as if I would go to Lake Superior, one of the biggest lake in the United States, and I would measure the height of the lake as I would remove one bottle of water from it. And I want to like measure the difference that makes on the lake. So it's insanely precise and like measurement that you have to do. And so that's why it took until 2015 to find them. But now we have it, so that's great. So to summarize this first part, the most important parts to remember for the remaining talk is that black holes form when massive stars die in these supernova explosions. And that since 2015, scientists can detect and observe these black holes through mergers of black holes with detecting gravitational waves. And these waves are so difficult to detect that we can only measure them from these supermassive objects, such as black holes. And so to kind of go back to this big picture in the beginning about exceptional marriage in the stars, well, we've maybe answered the first part, the second question, which is how many black holes live in space? Well, before we didn't know this well, but now that we can detect gravitational waves in 2015, we might actually be able to answer this really fast as we're really observing many, many more black holes in the coming future. And with that, we're going to the first break, and I wanted to ask if there's any questions.
Feel free to write your questions in the chat. If you're on Zoom, you can ask to be unmuted via chat as well. If you're on YouTube, you should use the live chats on your right-hand side. We'll wait a little bit to see if there's any questions. All right, I see one question from Yulia. Could you reiterate, how did you derive the number of black holes from the number of stars in the Milky Way?
I see. That's an excellent question, and it's actually not such a trivial answer. So I would actually say that the true number of black holes is currently not well known. So this is also one of the reasons why we're trying to find the answer through detections. A way that this number has been estimated of 100 million that I quoted is that we kind of know how many stars are formed each year in the universe. And we know how many of these massive stars are formed versus these more sun-like stars. And if you combine that with the knowledge of how long a star lives, you can calculate, okay, so how many massive stars were born each year, how many of them have already died, and then how many black holes must there be. And that's how you get to that number. Yeah.
All right, we have another question too. Yulia, thanks for your answer. This is from Dana. Does the Milky Way have more or fewer black holes than other galaxies?
Ooh, that's also a good question. So I think it actually has a little bit fewer of these black holes than other galaxies. And I think that's mostly because our Milky Way is already pretty old. So a lot of stars that are currently forming don't let's say how I best explain this. So how many black holes form is a little bit dependent mostly on like the properties of your galaxy and how big it is. And I would say the Milky Way is like a typical size of a galaxy. So in that sense, I would say there are galaxies with many more black holes if you have a much bigger galaxy with more stars, and there are galaxies with fewer black holes. At the moment, our Milky Way is not forming as many black holes like currently because it's not. It used to form many more stars than it's doing now. So if you would look at a galaxy that is forming many more stars now, you would also see that it's forming more black holes around the same time.
Any more lingering questions before we take a short break? If you have the questions over break too, you should feel free to write them in the chat and we'll definitely get to them. So we'll take a 5-minute bio break. Let's be back at 7:05. Back in front of their computers, excited for the second part of our talk. And hope you pondered if you know any non-single stars. But we'll hear more from Flor now. It's all yours, Flor.
Thank you. Yeah, so welcome back. We're gonna start the second part of this lecture, which is all about how some stars live a happily ever after in a couple, and why most don't. But let's first see. So where were we? So we can now, since 2015, detect those gravitational waves from a pair of colliding black holes, like this picture shows. And so these black holes, they are kind of these fingerprints that can tell us something about the history of our universe and how these black holes lived and died. But in order to learn something about that, we first need to know the following question, which is, how do you actually form such a pair of black holes in our universe? And so again, I'm going to put on this space detective hat and I'm going to think about, how do you make such a pair of black holes? So I told you that black holes form from a massive star, from the death of a massive star. And so it's reasonable to think that maybe to form a pair of black holes, you need to start with a pair of stars, like this is showing, which are maybe starting as a pair and can then form as one explodes in a supernova, forms a black hole, the other one forms in a supernova, another black hole, and can form this pair of black holes that then can eventually collide and produce the gravitational waves that we can see today. But there's kind of two main questions that are still to be answered before we know this happens in our universe, which is, do we have many of those pairs of stars to begin with? And second of all, if they exist in our universe, do they actually form pairs of black holes? Well, let's start with the former. Do we have many of these pairs of stars? Well, do you know of any pairs of stars? You might have thought about this. And so if you would ask me, I usually kind of come up with two examples. So the first one you might be familiar with is Tatooine. I don't know if you've ever watched Star Wars, but at some point you see this planet and where there's this beautiful sunrise or sunset with two stars that looks a bit like this image. And so these type of stars actually exist. And if you would make a video image, it looks something like this, where it's showing indeed this bigger star that is companioned by a smaller red star. And then surrounded, you can actually even have planets, such as this planet that it's shown in the video, which I think is really cool. And so these exist in space. And if you would live on such a planet, you would actually see two stars on the sky sometimes instead of one, as in Earth. And it would look something like this picture shows, where it's showing you the orbit, where in this case you have two stars orbiting each other, the yellow and red one, and then a third planet orbiting the two stars in a big orbit. But you can also have a planet actually orbiting one of the single stars in such systems. Now, another example is if I look at the night sky, you can often, in the Northern Hemisphere, you can see this constellation, which is called Orion, with this like beautiful belt, and it looks like it's hunting. And actually one of the stars, this one, is Sirius. And Sirius maybe looks like a single point when you look at the sky, but it actually consists of a double star system, where one is a star almost like the sun, and the other one is a white dwarf that are orbiting each other. And so they're actually two stars. And if you have a big enough telescope, you can actually see it. And so this is a question that I like to poll you on. So imagine you're walking outside and you're looking at the night sky and you see all these points of lights. But I just told you that, for instance, if you look at Sirius, it's not, you maybe see a single point, but it's actually a double star. So what fraction of the stars in the night sky do you think are like Sirius and are not actually a single point, but are a double or multiple system? Do you think it's A, between 0 and 25%? B, between a quarter and half of the stars that we can see? C, between 50 and 3/4 of the points in the night sky? Or D, almost all of them? See, there's some consensus. A lot of people are saying A. There's one brave person going for D. Let's see. yeah, you can see. So interesting. Um, so actually, no one had it right this time. Because the real answer is C. It's about 2/3 of the sky, stars in the night sky. So if you go outside and you look at the different points that you see, actually 2/3 of them are not a single star, but they're either a double or even multiple pair. And so this is definitely a little bit biased because the stars that we see in the night sky, they're typically the brightest stars nearby. And bright stars are massive stars, and they actually typically form in pairs or multiples. So that's why maybe in the overall galaxy, it's about 20%, but the skies that we see in our night sky, it becomes 2/3. So a lot. And I think that's pretty cool. Like every time I look at the night sky, I always try to imagine that actually a lot of them are these dancing stars that are dancing around each other. So to define this, so a pair of stars is what I call a binary star, where binary stands for the two, the pair. And so this is a star system that consists of two stars orbiting around a common center. They often appear to the eye as a single point, but they're not. And if you would have a good enough telescope, you would actually see it. And as I said, it turns out that most of these massive stars that we need for black holes are actually born in a binary system, namely about 70%. And they can also, these massive stars can also live in systems with more than two stars. So I think that's pretty cool. You would actually have three suns sometimes rising on the sky. Would be a fun next Star Wars movie. So just to give you an idea of these scales, how close are stars in a binary system? Well, imagine that we scale our solar system down such that our sun would be the size of a cabbage. This is a scale of 1 to 10 billion. So 10 billion centimeters is now 1 centimeter. In such a system and scale, the Earth that we live on would actually be less big than a grain of salt. We're that small compared to the sun. And if you would then look at the distance between Earth and the sun, or between two stars in a binary, this is about the same, and it's about the distance of a street, for instance. So imagine that if you're in a pair of stars, that you're a cabbage at the start of the street, and then your companion cabbage or star is kind of at the other side of the street, and you're orbiting each other and kind of like dancing around each other and being in love in your relationship. Now, this is kind of interesting. Okay, so this is what a pair of stars, how close they are and how much they love each other to like be this close. But typically stars aren't this close. And for instance, to give an example, in the same scale model, how far would actually the next star be to our sun? So our sun is single, doesn't live in such a pair, and its closest star is Proxima Centauri, which is, it's not in a pair way, but it's kind of the next neighboring star. So in the same scale model, how big do you think the distance is between those stars? Is it a couple of feet? Is it the length of a soccer field-ish? Is it the distance across the USA? Or is it even bigger and it's about the diameter of the Earth? Ooh, a lot of different answers. Interesting. So it's very spread out between B, C, and D, with a small majority going for C. And this is actually correct. So the right answer is that it's the distance between, for instance, Boston and say California. So imagine that if if you're a parent star, you're pretty close, you're like friendly, you're like across the street. But then your actually next neighboring star is, you were here in Boston where I am as a cabbage, and then the next cabbage is literally in California. And so this is also why stars typically don't collide. And these pairs of stars, they're pretty special and they're like super close, and yeah, they have to be a good pair and love each other to survive such close relationships. Yeah, so the right answer was C in this case. So, okay, but let's go back to this main question. We want to form pairs of black holes by starting with pairs of stars. And so we just discovered and discussed that we do have many of such pairs. But now the big question is, do these stars that are born in pairs, do they form pairs of black holes that can collide and merge? Well, this is a little bit tricky. Because if we go back to our model of how stars live and die, we now start with two of these massive stars, as you can see here. And the same happens. So at the end of the life, the star becomes big, goes supernova, and explodes to become a black hole. However, although most of these stars are just born in a pair, the majority of them during the supernova has a stellar breakup. And that's because this explosion is so explosive and energetic that it breaks up the pair. And you can imagine that, if you go back to this cabbage at the beginning of the street and the cabbage at the other side of the street that are orbiting, if one of them is losing a lot of mass or is exploding partly, that, they both kind of decide to go their own way because these relationships are very fragile, just as in pairs on Earth between humans. So in most cases, these pairs of massive stars actually don't form pairs of black holes because they actually go away from each other and disrupt before becoming that during the supernova. And only very, very rarely, in 0.0001%, so 1 in 1,000 or so, these stars can survive the supernova. The other one can also go supernova, and then they can form a pair of black holes. But their relationship has to be really, really strong, and we need to find what makes some of these relationships so strong. And to give you a visual representation of what that looks like, is this video. So here you can see a pair of stars. And we also already discussed that actually in some cases you have other things that can happen, such as one of the stars can actually eat a little bit of the gas of the other star, which we saw in this X-ray black hole. So this is what's happening here. So this white star has evolved and kind of become this big giant, in this case a white giant. And the other star can actually start eating material from the other one. And so this is another extra thing in their relationship that makes things complicated and basically causes that most of these pairs don't end up as these nice pairs of black holes. But eventually, when the star ends its life, which you'll see now, it ends its life in this supernova. And these are so explosive that most of these pairs will break up. And this is how bright these events are in real life. And so to conclude this part is, do they form pairs of black holes? Well, yes, but only very rarely. So only maybe 1 in 1,000 of these massive stars that form in pairs actually have a tight enough relationship that they can form these pairs of black holes. And so just as here on Earth, how most relationships that maybe are started don't survive, actually when you look at stars in space, it's even worse. And only a very, very, very small fraction of these stars that are born in pairs actually survive and stay together for billions of years to form these colliding black holes. And with that, I'm going to ask if there's any questions at this point.
Again, feel free to ask your questions on the chat. on Zoom or on the live chat on YouTube. We'll wait a little bit.
Documents imply
in the existing ticket.
All right, we have one question. Do both stars need to supernova at almost the same time? What happens if one star turns into a black hole and its partner does not?
So those are great questions, Dana. So they don't go exactly at the same time, supernova, but typically there's like a couple of maybe million years between it. And that mostly depends on that's mostly because like one of the stars usually starts out a bit more massive or less massive, and so they die earlier or later. And yeah, that's another good question about do they always become a black hole? Well, no. If, for instance, you start with a pair of stars where one of them is lower mass, it doesn't form a black hole, and you can actually end up, if you want, with like this compact star black hole pair. But there's also a lot of other combinations that can happen. So there's definitely more variations in what the outcome can be. I just think the pairs of black holes are the most fun and exciting because we can actually observe them with gravitational waves. And a lot of these other pairs, they might be more difficult to detect because they're less massive. And so they produce less of these waves in space.
Awesome, thank you. We have another question. This one's from Cynthia. What happens if only one star in a pair is massive and the other one is only the size of our sun or even smaller?
Oh, great question again. So I would say that in most cases, the same happens. So when the star explodes and forms a black hole, the double star system breaks up. And so you would have kind of one black hole pondering around in the universe and one sun-like star pondering around in the universe. In some cases, also rare cases, 1 in 1,000 or 10,000, they stay together and you can have this like compact star or sun-like star black hole couple. So a star like the sun could be in a couple with a black hole. It's just very rare, and our sun isn't, as far as we know. So it would be fun. Great question.
I have a question too, and on breakups. Do breakups only happen during supernovas, or can stars break up at other times in their lives?
Great question. They can break up in many occasions. So for instance, during some of this mass eating happens, it can also happen, but most of the breakups happen during these explosions, just because they're so energetic, and it's kind of as if you're, holding a rope with your partner over these like couple of meters as a cabbage, and then during this explosion, this rope is like cut or like hurt or so. So it's just much more damaging to the relation than a lot of these other events, I would say. So yeah.
Awesome. Oh, yeah, this is another question from Yulia. I was actually wondering this too, so thank you. Could you elaborate on how the eating exactly works? Does one star attract light from the other?
Oh, that's a great question. And yes, I didn't put full detail on that. So it's close step a little bit different. So basically what happens is that you start with 2 stars, but as one of them like expands, becomes really big, and since they're so close compared to like say a star with the next star, some of this mass from that one star that is expanding can kind of reach the other star or like flow to the other star. So it's really a combination of that these stars are relatively close to each other, and then one of the stars becomes really big, and so big that some of this gas from the envelope can flow or move to the other star and be attracted by the other star. Yeah, that's a great question.
That was so cool. Do we have any other questions? If not, we'll take another short break. And you can ponder how you play Battleship, how competitive you are when you do play Battleship during this break. We will be back at 7:30, so 4 minutes from now. Go get water. How's everyone doing? Are you back to hear more about black holes? And we'll see its connection to the game Battleship.
Thank you. Yeah. So at least I think this is like one of the most exciting parts, but that can be very personal. So let's get into the last part, which is all about finding the secret behind these matches made in heaven with the game Battleship was shown. And so where are we at? Well, we discovered we can observe these gravitational waves, and these learn us about how many black holes there are in space, and for instance, our own Milky Way. And the other questions that we want to ask is that we know these gravitational waves come from pairs of black holes, and that these black holes now form from these pairs of massive stars that live billions of years throughout their universe. And so this main question is, how did these stars form? Which of these stars can actually have these everlasting happily afters? What's their key to that ingredient? And what can we learn about that for our universe? Well, so this is the main question I want to focus on. And again, I feel like this space detective, because although we can observe these black holes, since they form in these billions of years, we cannot directly see the stars they are formed from. So we basically only see the deaths or the remnants, which are these black holes. And now we want to figure out, like a detective, how they died and how they formed, and which pairs of stars formed them. And so in order to do that, I, for instance, do that using computers. And so instead of looking at those stars, which is impossible, I try to, with a computer, calculate what they could be like before they form black holes. And doing this works a little bit the same as playing the game Battleship, we'll see. So to explain what is a game of Battleship, well, you probably know it. You play in a game that looks something like this. So you have a grid, which is 10 by 10, with, for instance, on the x-axis A, B, C, D, E, F, G, I, G, and on the other axis, like numbers. And then your opponent has placed ships in a secret location, and the goal of the game is to guess the location of these ships. And so what you, for instance, might do is that you guess a square. So it's your turn. You guess, for instance, C4, and your opponent will tell you it's a miss in this case. It wasn't one of the ships. And so you continue, and you, for instance, now guess a different one, say F and 8. And in this case, your opponent will say, oh, that's a hit, and you'll continue the game. And ultimately, you're trying to find all the ships as fast as possible, and in as few as turns, so that you win from your opponent. Well, this is a little bit the same as what I do when I try to find the key to those everlasting happily afters in space. But in this case, it looks a little bit different, and I'm playing against or with a computer. In this case, I'm not trying to find ships in this grid, but I'm trying to find the properties of stars, so hypothetical stars, that can form these everlasting happily afters and form a pair of black holes. And so I might, for instance, now have on this axis different hypothetical stars that represent stars in our space, our Milky Way. So for instance, stars with 5 times the mass of the sun, or 10, or 15, or 20, or 25. And then on the other axis, I, for instance, have the mass of the other star. So also 5, 10, 15, etc. And then my question is, which combination, which pairs of stars can have these happily ever afters and not have a stellar breakup, but form a pair of black holes? And so how this works is very similar. In my case, I take my turn, and in my turn, I start with, for instance, a binary star, so a pair of stars, where one is 15 solar masses, so 15 times the mass of the sun, and the other star, the companion, is 20 times the mass of the sun. And instead of my opponent, I put this into a computer. And so my computer will then do these calculations. And for millions of years and billions of years, track these stars and see how they live and die. And in this case, they might actually find that it does form a black hole in a supernova, but that then this pair disrupts, and it's one of these breakups. And so my computer will tell me, oh, actually, this pair of stars, it's a stellar breakup. It didn't form a pair of black holes, and it's a miss. So no information here, and I will be sad because I don't learn anything. However, I might try a different system next. So maybe now I try this system, which can then be a pair of a star with 30 times the mass of the sun in combination with a star with 40 times the mass of the sun. And in this case, if I ask my computer, can you compute it? It will again do all the calculations, but in this case, it might actually find a pair of black holes that merges and can form gravitational waves. And so after this calculation, it will tell me this is a hit. This was a pair of stars that can form a pair of black holes. And I'm happy because now I found one of these successful relationships. However, there's a problem. And the problem is that this takes a lot of time because doing these computations on my computer, each calculation, so calculating one pair of stars and finding whether it's a miss or a hit, takes about a month. And that's because we need to calculate how these stars live over millions to billions of years. And that's a long time to keep track of all these calculations for what the temperature is, how they're doing, whether they're eating any mess from each other, etc., etc. So it's a lot of calculations in the computer, and it takes a month. And so, as you can imagine, to really find these these black hole mergers, we have to like look and do all these computations. And so, to make it feasible, we want to know, like I want to know as an astronomer, how do I minimize these numbers of turns that I need to take to find enough of these red crosses and hits that form my secret to forming a binary black hole that can merge. And so I want to minimize these number of turns and thereby minimizing the cost of my computer. And so actually, well, we saw a lot of similarities with Battleship. So my question to you actually, and maybe someone wants to unmute and say what they think. How would you play a game of Battleship? How would you minimize your number of turns against your opponent?
Feel free to write in the chat, or you can also unmute yourself. Nobody plays Battleship? I can say my strategy if that helps. I think what I do is I hit, if I decide on a point, if I get a hit, I'll try to stay around it and close to it. And then if I get a miss, I'll try to go somewhere completely different, assuming that I'm like in the wrong place. Oh, there's one in the chat too. I start to create a grid, maybe a 3x3, covering the whole board, but spread out. That's strategy.
Yeah, no, thanks for that input. That makes a lot of sense. So I agree. I think that's how I also usually play it. How I actually wouldn't play it is probably what I would call random shooting, where you would completely randomly guess the next point in your grid, so in your Battleships game. Because it actually turns out if you do it this way, so you just each time you completely randomly choose the next guess that you're taking. Out of the 100 possible locations, it actually takes about 96 turns to complete the game. So you almost need all 100 to complete it. And so instead, as you also mentioned, how most people instead play the game of Battleships is that they maybe start randomly shooting. But once you find a hit, like here, you actually start exploring around it. And so this is what I would call explore and refine. And it turns out, if you do this, it's somewhat faster, but how much faster do you think this is? Do you think it now takes about 25, 45, 65, or 85 turns to complete the game? Ooh. See a lot of spread in the guesses again. A lot of you think 45, that would be cool. So 25 would be a very quick game. Oof, I can see it. Yeah, so that's great. The correct answer, actually, no one guessed it, is 65. But it's hard. It's pretty hard to notice or so. You'd have to actually do a simulation and see how this works. So yeah, but as you can imagine, then if you would play against a person who does it randomly, you'd actually almost always win because you're so much faster still than someone who doesn't at all use this tactic. And so this is exactly what I actually developed in 2019. So we had this problem that this is super expensive and that we want to minimize the cost of the number of turns to discover it. And so I actually developed a cool code to do this, which we called stroopwafel. So after one of my favorite cookies, for good reasons. And you can see this is the logo. You can see that it has a little bit of the Battleship in it. That's why we chose it. And to give you an idea, so this is actually from the paper. It's a scientific paper that's published, and it actually explains that, well, how it works is pretty similar to playing game Battleship. So yeah, I thought it was pretty funny and a good example of how playing these games can be really helpful to me as an astronomer as well. It can be a tool to learn about these stars. However, there's also some extra challenges. It's not exactly the same as playing a game of Battleships because, as you probably imagine, then people would have already invented it before 2019. So there's a couple of extra problems that actually I had to take into account. So first of all, as you probably maybe already wondered, these stars and these binary systems, they don't just have these two properties of a mass and another mass, but they actually have many more axes. So in real life, you have all these extra axes that are, for instance, what distances the stars start with. So what is the distance between the two cabbages at the start? That varies among stars in our space. And so in our Battleships game, where we try to find the stars, we also need to vary all these extra axes. And so it becomes kind of like playing a game of Battleships in 20 dimensions, if you would. Another issue is that actually these areas or boats are not well defined. So in my case, when I asked this computer, the stars that form a binary black hole merger, so a black hole collision, they're not going to perfectly form these ship-shaped areas in my grid. So they actually might look something like this with some blobs everywhere. So that's also hard. But as you, Dana, for instance, already mentioned, we can actually also use some of these other game tactics to help us. So we already discussed that we can use this explore and refine. So this is also what I do in my computer. I maybe start randomly, like these gray points, but once I have found one of these stars that forms a binary black hole merger, I search around it and I have many more hits. But as you already saw here, you might actually, at the start, have guessed, or in 2 turns, guessed locations that are very close to each other. And so in real life, we want to avoid it. So something that we do is we do something that I call Sudoku sampling. So you basically divide your space or your grid up into, for instance, 9 little grids, or 4 in my case. And instead of randomly completely guessing, you started kind of like guessing one randomly in one corner, one randomly in one corner, etc., etc. And so that actually helps even further minimize the number of turns. And then there's one other thing that you can, in addition, do, which is, in these cases, you have a lot of these guesses here to try and find these blue boats in my case. But as you can imagine, maybe I actually didn't have to guess this middle cross. But if I actually had just guessed these outer layers, I could have guessed that in the middle it will also be a hit, because it's unlikely that these boats have holes. So in real life, another extra thing that I can do is, like, I don't have to actually compute these 2 points, but I can just guess them from knowing that around them they're all forming binary black hole mergers. And so doing all of these things really helps me as a scientist. And so instead of having one calculation take a month and then doing all these calculations take several years, like it would usually take like hundreds of years, I can actually do them in total in like a couple of months actually. And so this actually makes it possible to try and beat a space detector and find these black hole mergers. And so we can do this really with these kind of like board game tactics that I think are really cool. And so to just go back to these main questions that we asked. So in my case, I'm really interested in black holes in space. I want to know how many there are. And we can do that now by using gravitational waves to detect them. But other than that, I know that these pairs of black holes are one of the things in space that live the longest through the history of our universe. And so by knowing that they form from these massive stars and observing them, and then by comparing them with these computer calculations, we can actually discover how they must have lived in their past. And we can be a space detector and find out who they are. And so to summarize all of this, I hope what you take away from this lecture today are the following points. From the first part, that these black holes form when massive stars die, and that since 2015, we can detect these using the mergers of 2 black holes that produce those gravitational waves. Now, we saw in the second part that we think those black holes form then from a pair of massive stars. And we know that these pairs of massive stars are common in space, and that in very rare cases, they can form these pair of black holes that can then collide. And in the last part now, we discussed that by comparing this with computers, we can find and study these matches made in heaven and find what the key is. But we do need these cool tactics like the Battleship game to actually find them in a short enough time. And so by doing all of that, I hope we can hopefully answer these questions soon as more of these detections come in. And hopefully we learn something about both black holes, but especially about our universe and the history of our universe. And with that, I'm going to say thank you for listening and asking if there's any questions.
Thank you so much, Floor. That was amazing. Let's wait for questions. Again, feel free to write in the chat. You can also ask to be unmuted if you want to ask it verbally. And you can ask it both on Zoom and on YouTube. And we will get to them. Ooh, we have one. I'm curious about the computer program you used to find these pairs of stars. How can you know what will happen if we only have a few examples of black hole collisions that we've observed?
Ooh, great question. So I would definitely say that you're right that we don't know a lot about them yet, since today we now know about like 50 of those black hole mergers. But actually, these detectors are still looking, and the number of these black holes that we see is rapidly increasing. So it's expected that in the coming 5 years, we'll actually already have many thousands of such mergers. And so hopefully, such a big observation of many black holes will actually help us then learn about what these black holes are like and what the different of stars are like. But yeah, we'll need more observations. So a little bit of waiting will do a lot of work for us. Yeah.
I also have a follow-up on your computer program. So now that you've played a bunch of Battleship, are there certain couples that work out really, really well in between stars? Like, like close masses, close to certain properties that work really well to create these matches made in heaven?
Yeah, so it's a lot of fine tuning I discovered. So they need to be not too far apart because the further they apart start, the easier they are to disrupt and like break up during the supernova. However, if they start too close, they like when one becomes bigger at the end of its life, like the other one basically can almost eat the entire companion star. So it's almost like a little bit obsessive eating from your partner. And so these stars also won't form a pair of black holes because basically just one star will consume the entire relationship and eat the other stars. So yeah, it's kind of a fine-tuned distance in between, I would say. A healthy distance, just like in relationships, I guess, on Earth, that, you probably want to have a healthy relationship where you give some space to each other, but you still want to be close. Yeah.
I like that. We have so much to learn from stars. We have two more questions in the chat. One is from Mike. One assumes that the planetary systems of these couplings are inconsequential, as are they to the organisms on them. So like these planetary systems, the babies of these stars that are around them.
Yeah, what's the question? Sorry. What are they inconsequential?
I think the question is, are they inconsequential or not? Like, how do so these couples have babies, which are the planets? Do they get affected? If they do, how? Do we want them to explode? Maybe we don't.
That's a great question. So actually, to date, astronomers don't know. We think that during this supernova explosion, some of the planets will also get ripped apart or disrupt. But in some cases, the system might stay together and the planet might also survive. We haven't observed any of such systems. So you would, for instance, see it if you see, for instance, a pair of black holes with a planet. But it might be detectable in the future, but probably you need to have even better detectors to find this small planet around a pair of black holes or another pair. But yeah, likely it exists, and I think it would be super cool to be a planet around like a pair of black holes or so, or something similar, like those complex stars. Yeah.
Super cool or super dangerous?
Well, we probably wouldn't survive, especially black holes. It's there's no light, so there's no heat. So it would be a very cold planet. But yeah, maybe around some of these other stars, it might be possible. Yeah.
That's awesome. There's another question. Do we think that there are a lot more gravitational waves passing through the Earth that we can't detect?
Oh yes. So basically, at all the time there are gravitational waves passing through Earth. And actually, if I would dance around with someone, we also create gravitational waves. But most of these are either too small and too tiny to detect, or we cannot detect them because they don't have the right wavelength or like the right type of emission, like light that we can actually see. And so the ones that we detect are from these black holes because they're so much bigger compared to if I would just dance around with someone. But there are actually people building a new detector in space. that can maybe detect gravitational waves from different sources as well, like from galaxies colliding. So I think that would be pretty cool. But yeah, there's probably a lot of gravitational waves passing through me right now. It's just I don't measure it because they're so tiny in displacement. But yeah, it might be like different, feeling some space waving through me. Yeah.
We'll wait a little bit for more questions. Please feel free to write them if you have any. But in the meantime, I'm going to post a link to a feedback form that we have. It's very short. We would love to get your feedback. We'll keep doing these lectures. Our next one is next week, same time. It'll be a lot about energy, so you should come to that as well. So this form is like, how did it go? Is there certain topics you want to hear more about? So please take a few seconds to fill that. And we'll wait a little bit more if you have questions. You're getting lots of claps and lots of things.
Yeah, and thanks so much everyone for listening. I appreciate it. Especially in a Zoom world like now.
We can't dance around each other, unfortunately. Create small gravitational waves. All right, if there's no other questions, we might end our event for tonight. Thank you so much for joining us. Please join us for more. This lecture will be living on our YouTube page, so if you want to rewatch it, you should feel free to do so. And thanks again.
Thanks, everyone. Have a good night.
Goodbye, everyone.